Hi everyone, this is Will. Today we're going to be discussing the visual pathways of light through the eye all the way to the brain. So to start, what I'm going to do is take apart the eye and then reconstruct it and show you how light goes through each layer. So to start, light goes through the tear film. The tear film is located right in front of the cornea. Then it goes through the cornea. The cornea consists of 5 different layers. We have the epithelium, we have the Bowman's layer, we have the stroma, we have the Decimus layer, and the endothelium. So after going through all 5 of those layers, we hit the anterior chamber. Now the anterior chamber is a little pocket between the cornea and the pupil. This little pocket, known as the anterior chamber, is filled with aqueous humor. As long as it's clear, it keeps on going through to the pupil. Now the pupil, I'm sure you've heard these two terms, dilation and constriction. Dilation is where your pupil gets really big to allow more light to come in. Then constriction is where it gets really small to limit the amount of light that goes in. This is controlled by the iris. The iris is the colored part of the eye, and it's controlled by 2 muscles known as the sphincter and dilator muscles. So these 2 muscles control the iris, and that controls how much light goes through the pupil. Then we have the intraocular lens. The intraocular lens is a biconvex lens, which means that there are 2 convex lenses on this lens. And what happens, whenever an image or light goes through it, it flips upside down. So if you're looking at a candle, it flips. If you're looking at a baseball player, it flips. If you're looking at a hat, it flips upside down. Whatever you're looking at flips. Don't worry, we'll flip it right side up later on. Now, we go through the vitreous humor. It is a watery substance. As long as it's clear, keeps on going through and focuses on the retina, or the back of the eye, the inner layer back of the eye. Now, real quick, I just want to review everything. Hits the tear film, goes through the tear film, goes through the 5 layers of the cornea. After that, goes through the anterior chamber of the eye and through the aqueous humor. Then it goes through the pupil. After going through the pupil, it goes through the intraocular lens. After going through the intraocular lens, the image flips upside down and continues to travel through the vitreous humor and focuses on the retina. Now, I'm going to try to show the retina best I can with my model. My model is not really the best for showing it, but the retina is that pinkish, orangish layer right there in the back. For argument's sake right now, I'm going to only use the top part of my eye model because it's easier. It's the pinkish area. With that being said, there are 9 different layers of the retina. The inner limiting membrane, the nerve fiber layer, the ganglioid cell layer, the inner plexiform layer, the inner nuclear layer, the outer plexiform layer, the outer nuclear layer, and the external limiting membrane. From there we have the photoreceptors. So I'm going to pause real quick at the photoreceptors. They're really important. They contain what's known as rods and cones. Rods are helpful for movement and night vision, whereas cones are helpful for color. So the C in cones and the C in color, they kind of connect. You can remember it that way. But they help with color vision. The cones help with color vision specifically. Then we go to the retinal pigmented epithelium. This is like a pit stop for your light, for the image, for whatever you're looking at. It's like a pit stop. It's going to stop, regenerate, get some snacks, do its thing. So what's going to happen here? The image is received by the retinal pigmented epithelium, or the RPE, and the image is then absorbed by this layer. This is a fascinating layer. I'm not going to a bunch of detail with it. Don't worry. This image is then converted by the way the outer rods and cones. So remember the rods and cones, rods for movement and night vision, cones are for color. They're converted into 3 different forms of energy, starting with light energy, then chemical energy, and finally visual energy. From there, the image causes a chemical change in the visual pigment at the rods and cones. Remember, we're showing the outer rods and cones, and it energizes and stimulates those rods and cones. This stimulation then creates an electrical impulse. Keep in mind, we're still in the retina. The retina is such a fascinating small layer, but does such an important job for the eye. Now, the stimulation creates an electrical impulse, like I said. This impulse then causes a first synapsis, or an interaction. It's an interaction, and it's formed in the outer synapsis layer. Now, this formation causes the rods and cones to take the image and change it into a visual nerve impulse. This visual nerve impulse then travels back through those 9 layers. So like I said earlier, it's like a pit stop. So it stopped there, and then it travels back through these 9 layers, and so they travel back to the photoreceptors, through the extended limiting membrane, through the outer nuclear layer, through the outer plexiform layer, through the inner nuclear layer, through the inner plexiform layer, the ganglioid cell layer, the nerve fiber layer, and then the inner limiting membrane. So it travels right back through those layers after getting its snacks and regenerates and gets a few drinks, goes to the bathroom, you know what I mean? It does its thing, little pit stop, and then travels right back through. From there, after traveling back through those 9 layers, the image travels to the middle cells of the retina. At the middle cells, the second synapsis occurs. The second synapsis is located in the inner synapsis layer. So the first one, remember, was the outer synapsis layer. We go back through the retina to the middle cell. Now the second synapsis occurs in the inner synapsis layer. Keep in mind, we are still in the retina. We haven't gone to the optic nerve yet. We haven't gone to the front of the eye. We're still in the one layer known as the retina. Now, the image gets transferred by electrical impulses from the photoreceptors. Remember, the photoreceptors have the rods and cones to the optic nerve. Now, I'm going to put my eye model back together. Give me one quick second here. The optic nerve is this pole out the back of the eye. It contains millions of nerve fibers. With that being said, the optic nerve then travels out, and it goes to what's known as the optic chiasm. The optic chiasm is where the 2 optic nerves connect. Keep in mind, I say 2 because you have 2 eyes. So each one comes out of one eye, comes out of the other eye, and then they form, and then they connect together. It's like connecting a clasp on a necklace. On the back of a necklace, you connect a clasp, and it comes together at that clasp. Now, real quick, something that's really important about this part. There is a nasal and there is a temporal side. The nasal, closest to the nose, crosses. So those nerve fibers cross. On the other hand, the temporal side does not cross. So they do not cross. With that being said, I want you to think of it like this. And I am going to kind of discuss the retina a little bit for this part because I feel like it's important. It's important for us to kind of understand how this works. The left side of the retina. So, left side of the retina. That information goes to the right visual field. On the other hand, the right side of the retina goes to the left visual field. And this visual field is in the optic chiasm. Now from there, these impulse signals that are created all the way back at the RPE travels through what's called the optic tract, all the way down to the LGN. The LGN consists of 6 different layers. And this is also where the third synapsis occurs. So remember, we had the first synapsis, we have the second synapsis, now we're on the third synapsis, which occurs in the LGN. From there, the electrical nerve impulse continues to make its way to the brain by the way of optic radiations. These optic radiations travel and they take the image all the way down to the visual cortex. The visual cortex is the brain's main processing center for vision, and it is located in the back of the brain in the occipital lobe. In the occipital lobe. From there, the visual cortex divides the information into two different streams. The ventral stream tells you what it is, whereas the dorsal stream tells you where an object is and how to react to it. From there, this is where the image is finally stored in the brain. Thank you very much.